done this already.
Yeah, you've done a bit of it.
He says before every single section.
No, you'd be surprised. You'd be very surprised about this. What happens here is
What's the probability that we
oh, there it is. What? No,
I'm surprised that the
what happens here is I want to ask you this. What is the probability of me taking a 6-sided die and rolling a 2? 1 out of 6. So the probability that I roll a 2 is 1 out of 6. Okay? What's the probability I roll a 3?
1 out of 6.
Were those completely independent of one another? Did the fact that I rolled one thing the first time have any bearing upon the fact that I rolled the second time? No, they're independent events. So what happens when you do something like that, if you want to figure out that you want to roll a 3, then the probability of roll, what did I say, 6? Let's do that. Well, the probability of rolling a 3 was what? 1 out of 6. Winner!
Did it really roll 3?
Yeah. So I have 1 out of 6.
What are the odds?
Now,
shut up there, Joe?
That was true again.
now what's going to be the probability of me rolling a 6?
I literally just looked at the odds.
Oh. What happens to those probabilities if I wanted those 2 events to occur? What do you think I'm going to do? Multiply. Yeah. I'm just going to multiply these through. So I get 1 out of 36. It's basically very similar to the, when we did the roll 2 die stuff, when you're just looking at the possible outcomes. There's 36 possible outcomes when you roll 2 die, because each die roll is independent of one another. So you just multiply the possibilities together.
Do they become dependent of one another if, like, you only roll second die if you get a 2?
Yes,
Okay.
and that's completely different. Okay, that's something different. That would be dependent things, and we're not going to get to that complicated, but along those same lines, you already wanted something else to occur for the next thing to occur. Yes.
Based on what I'm seeing on the board here, independent clauses you multiply and dependent clauses you divide.
I haven't done anything about that division at all.
You just said
I-
It looks like it's-
That is nothing like that. It's not a division symbol. Okay. I know. This means something, and I'll explain what that means here in a little bit. Okay. Don't worry about division. Okay. Don't jump to conclusions. Don't buy that math. Come on, you got to catch the reference there.
Is it that?
You don't catch the reference? Come on, you
Wait,
kidding
wait,
me?
wait, is it that thing with the phone booth and they jump to the Isle of Conclusions, that book?
No. It was Office Space. The guy jumped to conclusion. The mat. He had to roll the mat
I've
up.
only seen that movie once.
I thought you mean when the guy burns down the building in Office Space because he can't find his seat. Me neither.
I've never seen it.
You?
Yeah.
You will love it.
I've seen Office
You would
Space,
love
it's really funny. It's really funny, he burns down.
Oh, if Clay thinks it's funny, then I'm not gonna.
No, it's actually hilarious. Shut up, Zab.
You heard that too?
Colin can make fun of me.
I heard it.
Yeah. That's a good voice crack, bud.
Shut up, Val.
Same idea. Same idea.
Oh, that's it.
Probability, we're flipping cards. The probability that I'm going to flip over a card, and I'm going to guess that it's going to be the 7 of hearts. What's the probability that I flip this into the 7 of hearts?
1 in 52.
1 out of 52. So I get 1 out of 52. Then what's the probability? If I put the card back in here, reshuffled, taking another card, 1 out of 52. So is the fact that if I'm putting the cards back in the deck, changing any of the probabilities? And that's kind of the catch here. They're independent of one another because the number of cards here don't change. The number of cards doesn't change. There's still 52 of them here. Okay? When we get to dependent, something changes. Very subtle, and you'll catch it real quick. So like we said, dependent things occur when you have did I say independent? Yeah, I meant independent, I'm sorry. The independent things are when you have 2 events that you're looking at, or more events. Each consecutive event had no bearing upon the next one. Flip a card over, it's the 4 of hearts, put it back in the deck, 7 of spades, put it back in the deck. It's not changing.
So is that if you're to, the probability of you getting that 4 of hearts and 7 of spades is 1 over 52 to 1 over 52?
Yes, sir, because the card goes back in the deck
Oh.
with replacement. Then it's dependent that something else had occurred. And we'll talk about that, okay? Yes, sir?
If it's something that has more than 2 events, you just keep multiplying
Yep.
them together.
Yep, that's all it is. That's all it is. And you start thinking about, well, when we get into the dependent, you'll see that it's very subtle, okay? And it's so easy to pick up on. All we're doing here is when you have independent events, you're just multiplying together. That's it, okay? That's all it is. So if I'm looking at the spinning wheel of money,
Yeah.
yeah, nothing but the best for us. It is the spinning wheel
Look
of
at that
fortune.
square spinning.
Okay?
High tech.
So I am playing a game that involves spinning the money wheel shown. It is copyright, right? And I'm going, during my turn, I get to spin the wheel, not once, but twice.
Oh, man.
For you. Way to go. What is the probability that I'm going to get more than $500 in my first spin and then go bankrupt on my second? Well, that's I had to figure out the probability of getting 500 or better than 500 first, and then bankrupt.
How many wheels are there, like, spokes?
Well, let's figure out how many are 500 first. Here's 550, 5,000.
Everything that has an egg.
Oh, it doesn't?
Would you look at
Oh, look
that?
at that. I've done this 3 times today. I didn't even realize they were already labeled. You're just a smart man.
That's the bigger one.
So, I didn't want to say it. How many are happy?
1, 2, 3, 4, 5, 6, 7.
8.
8.
How many total are there? Well, let's count. Ready? 1 little, 2 little, 3 little spots, 4 little, 5 little, 6 little spots, 7 little, 8 little, 9 little spots, 10, this is getting old, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 spots.
Seem like good odds.
So you have 8 out of 24 of them is going to get you better than $500. Now, the fact that I've spun the wheel once doesn't have any bearing upon the fact of spinning the wheel again.
No.
No, how many of those then, if I go bankrupt, do I have? Out of how many?
Doesn't like where you start off affect where it's gonna land?
No, because they're all equally.
That's why you have a case.
I do have to had a case.
Like Ken Joe.
Didn't. So in this, now it doesn't really matter about where it's placed on there because everything is equally. Each one of those sectors is the same amount of probability of landing within it. So all you do is simplify your fractions and go. So you get 1/3, 1/12, and your answer would be 1 out of 36. So it's 1 out of 36 probability of spending more than 500 and then going bankrupt.
That's actually that's actually kind of likely, like not likely, but like
But
But like unlikely?
but
Like-
it's more than I thought it would be. Like it's better chances than I thought it would be.
like.
Totally, for sure. It's definitely.
All right. Now let's make it even more interesting.
Oh, man.
Yeah, so fine.
So I have face dice.
Is that Izzy?
It's yes, Izzy. We have Izzy.
We should use it.
So we have Izzy, Hannah, Jenna's in this one.
Oh, use the one of Hannah. That one's funny.
Yeah, that one's really funny. I agree. Then Hannah, Aaron's in there, and then good old Caleb at his face. So we're gonna find the probability of should go. Well, we gotta go with Jenna. 'Cause she's here.
No.
So how many faces are on the die?
6.
So we want the probability of going and landing on Jenna, and then. Hey!
Hey,
So we get the probability of rolling Jenna, Sorry. and then maybe getting red.
What are the chances we get red?
So probability of rolling Jenna and then getting red. Aren't those both independent of one another?
Yes.
Okay, so what's the probability of rolling a Jenna?
1 on 6.
Substitution.
And then what's the probability of getting red?
2 and something.
12.
Are you sure the 12 can show?
2 and what?
It's 2 out of 12.
What do you got, Major?
So isn't that 1 and 6, 1 and 6?
No, 1 6, so we just.
So what's the probability we're getting? Hey! Oh, we got a
Shot
Caleb.
Caleb in the face.
We got
Oh, he's got a massive pimple.
yeah. We got a Caleb and a.
Oh,
It hit red. It hit red.
I didn't
Oh,
land on red though.
but they were independent events. It's just anything I can think of just to throw. Use this as fun.
But you broke
Well,
one of the
it's the
arrows.
same chance as if you were to go above 500 and go bankrupt. 136. Right?
It's crazy how that happened. Maybe it's because I chose red. What about orange?
It's
This is how
One
it
and
is.
12.
So we've got Jenna.
Let's see.
Yay!
No, it looks halfway there.
And we got Jenna. Now what's the probability?
4 on 4.
Now we're gonna go orange.
Two slides. Go literally 2 on the floor.
And orange.
Hey!
Oh, now we get a red.
Now we get rid of it.
We got red.
So, but you get the idea, right?
Yes.
They're independent of one another. There's no bearing upon getting the first one to getting the second. The different one.
Red.
I wish you keep going until we get what we call.
Yeah.
Dependent.
It's a 1 in 64 chance.
When you're dealing with dependent, it's slightly different. What happens here is you say it differently. If A and B are dependent, that means B can only occur after A occurred. If A occurred, then B occurs. Okay? They have some connection to one another. So what happens is you say it as if A and B are dependent, the probability of both A and B occurring is probability of A and B equals probability of A times the probability of B given A. That's just saying that probability of B, this vertical line means given A has already occurred.
Wait a second. So just ignore it if A hasn't occurred.
Well, you'll see how it works really fast when I do a card trick. Well, not card trick, but a card problem.
You should see what they're doing on
Seriously. There's nothing up my sleeves. Now, let me say this a little bit differently now. I want to do the probability of getting a jack. Well, we'll go probability of a jack, then the probability
Liquid chance.
Shut up.
of a 4 without
What is the word in the middle?
replacement.
Then.
Bad.
Yes, read it. That says that.
It says told.
The probability of getting a jack, then a 4 without replacement. What that means is when I flip over the first card, I just don't put it back in. So now that right there means that it's a dependent probability because your amount to choose from changed. You guys probably did a problem like that in Algebra 1 when you had marbles. Marbles in the bag where you put them back in or you left them out. You were working with dependent probability. I'm sorry, and you're not crying in Algebra 2, so that's good?
My soul's dead. I have no more feelings.
All right. That's an Ozzy Osbourne song.
No, my two cars are rock.
So a probability of getting a jack is out of how many?
152.
4 out of 52.
So when I'm doing these compounding ones, or when I'm looking at this a lot of times, when there are I don't have to simplify it because calculators can do the work for me anyway. So just write it, there's 4 out of 52. Now, given that I've already picking, I'm from Texas like Val.
I already picking.
So, sorry, Al. I'm not putting this back in the deck. How many do I have left to choose from?
51.
So it'll be 4 out of 51. This is how it works with the lottery. Yeah, you're still multiplying. This is how it works in the lottery. The lottery, you think about, you've got, well, it's really easy, like the pick 4. Lottery pick 4, you've got 10 digits, 10 ping pong balls, and 4 hoppers. You want to get all the probability of each one of them to work. Oh, actually, I'm sorry. I'm thinking regular. Lotto. Lotto's the big game one where they have 54 numbers and 6 of them come
Is
out.
that really from the government access music? It's like.
Yeah. So you want it's the probabilities of each number coming out changes because there's less ping pong balls in the hopper. So the first one there's 1 out of 54. The second one's 1 out of 53, 1 out of 52, and so on. However many they're picking out. That's how these work. Because the probabilities change because they're dependent upon one another. The big difference you'll notice is this without replacement. That's how you know it's a dependent thing. Or it'll say something has occurred. Very easy.
If it's without replacement, that means the number on the bottom's going down. Doesn't that mean like it's less likely you're more likely to win?
Yes. Eventually, depending upon what the numerator's doing. Sometimes the numerator changes. For example, let's say you have the probability of heart, probability of diamond, and then probability of heart again. You're doing 3 cards. You're going to pick out 3 cards. You want to go heart, diamond, heart. So this is, I'm going to say without replacement. Okay, without replacement. How many hearts are in a deck of cards?
13.
13 of them. There's 13 out of 52. I don't put that card back. How many diamonds then? I don't put that card back. Now what is it? 12 out of 50. Very good. Because it has to become 12 out of 50 because this had to already occur because it's a dependent probability. And yes, you're just multiplying straight across them. It's that simple.
I'd make my lottery numbers like 131. That's
They didn't draw hard.
You're just basically you're getting 3 cards, and then the first one had to be heart, diamond, heart. If this was a heart, then that means that there's only 12 left for this one. That's all that means.
Okay, good.
Well, I got my
Did it draw hard, but you still have.
Then but it's still looking at what's the probability of it happening.
Okay.
That's what it's not the fact that your first trial failed. Go to the next problem. It's just what is the probability of it occurring. Okay, does that make sense? What we're going to do, because I know a lot of people are going to be gone on Thursday for that link stuff. I was hoping to get into some of that 12-6 stuff on Thursday. We'll probably do more of 12-6 tomorrow, and then play some of the game stuff that I had idea planned-ish for Thursday and Friday of a lot of these little quick worksheets, and you guys are going to test each other to see if you have ESP.
Would any of these games require no
7 of
cards?
spades.
Wrong, you don't have ESP.
Sir, if you would any of these games require
No.
no cards?
Yes.
Oh, ace of diamonds.
Just shut up.
3 of spades.
Try this again. What's the probability of the first card? All right, you're randomly selecting 2 cards from a deck. What's the probability of the first card is a face card, and then the second card is not a face card if you do one of 2 things. Replace it, calculate the probability. Don't replace it, calculate the probability. It's going to ask you to do both, with replacement and without. So if I'm with replacement, not a face card. Well, isn't it easier to count the face cards than it is not the face cards? How many face cards are there? So how many of them are not face cards? Aren't you using the complement? Not a face card first. So not a face card, there's 40 out of the 52. I'm not I am replacing it back in the deck, so the the denominator value doesn't change. So then how many of them are face cards? Out of how many? Now the difference between that and without replacement. It's subtle. The percentages change just ever so slightly. How many are not face cards? 40 out of 52.
40.
Now, given the fact that you've already taken one card out, what's the probability of getting the face card then?
12.
That's all it is, guys.
Well, did you notice that there's one less face cards than there is cards per suit?
What's that?
There's 12 face cards, and there's 13 cards per suit.
Right.
So it's really hard to get a face card. Yeah, I just noticed that.
What?
Yeah.
He just noticed it's
Yes, agreed.
Totally makes sense.
That's what he's saying.
What?
Yes, you're right. This is awesome.
Wait.
I missed it.
What is she making fun of me for?
Basically, what you've just figured out, Clay, that the number 40 is bigger than the number 12.
Yes, I know. That's
Congratulations, my friend. We all should give you a round of applause. Congratulations.
I think I should go.
All point?
You get 52 points.
Oh, she's up on
Clay gets negative 50.
Now, do you guys see how the decimal value there is very slight? I think they're within a hundredth or a thousandth or something like that.
I'm doing the math right now. 1 second.
They're pretty close, but that's what we're looking at doing here. Okay, it's very, very, very simple.
Do you want fractions or decimals?
Decimals are cool. Last little example here is you actually did
It's
this.
a 1% difference. Like
You did you did a little bit of this on that quiz. Wasn't so much of a dependent style, but you kind of read a table and figured out value. Okay. In this case here, it's a table of some great data from only 1998.
Oh, my, I wasn't even alive.
Out of this
Really?
class.
We're freshmen, Mr. Murphy. No, I'm not.
Find the probability the listed animal is a reptile. Well, how many animals are there total? I'll help you. 475.
475.
Very good.
That's bigger than 198.
There's 475 total. How many of the animals in this table are reptiles? Oh my.
What's the probability that I'll leave it on?
Well, it's really either you make it or you don't make it.
Nice.
No, what happened is he'll sidestep you.
You made it. Really didn't even.
Well, that's what I was saying yesterday. Isn't it like all of like this room and the size of that garbage can, and then isn't that the probability instead of 50-50?
There's
Emma?
the geometry.
We're gonna throw down.
There is, what you're thinking more is the geometric probability, and you're right. If you wanted to get into the idea of landing in just the recycling bin versus landing in the room, and not really.
I'm just gonna like show up in your driveway and like read.
Now, the next part here is a little bit different. When you read the next part, it asks about what's the probability that an endangered animal is a reptile? What are you looking at now?
14. It'd be 14 out. Whatever.
It's not going to be 475, because 475 is the total of everything.
No, that's other. That's not the
Just the total of
I thought it was total.
I don't know. Maybe marsupials, thank you. Or fish. Fish and insects.
What?
Instinct? Instinct, yes, they do have instinct. They have instinct to kind of run away from people. Well, fish don't really run, but.
475.
No, the 475, real quick question here, guys. The 475 came from the total animals. Now we're talking about just the specific endangered. I believe there's, well, just take these and subtract it from 475. It's quicker. I think it's 355.
Why don't you just add them all together?
You can do that too. It doesn't matter. Either one is the same. Okay. So when you're looking at problems like this, it's nothing more than just reading carefully if they're saying with replacement, without replacement, or going into a table telling you to be more specific when you're looking at data set. That's it. It's really quite simple. I hope.
It is.
You don't believe me? No homework. All right, how about this?
Really?
I will cut it in half if you get this one.
1 in 52 chance.
Oh, wow. Thank you.
I was off by 3.
You should cut it in a
You should cut it in half.
You can wish in one hand and the other. Goes up first.
I've never gotten that.
It's been a while since you said that.
I don't know. You can't put wish
Take a try it
in.
and then come back to.
You can't put wish. You can't put a feeling in.
What?
So it's do those, please. So far, most people have gotten, I'd say 75% of it done in about 10 minutes. So I don't see you guys not getting that work in. It's exciting.
I don't see you
Wait
guys
for
not
that.
lazy. Time out.